So I will start with a recall, but mostly what we are going to do today is going to be a little bit independent of what we were doing last time. So mostly what last time we were interested in was we take a graph lambda and we take a random function of the graph lambda to a or to rd, let's say, and we were wondering when phi satisfies the Lupu Markov property. So what was the Markov property? It was just saying, okay, extend your function to the whole metric map, and in the edges replace the values by Brownian bridges. So when do you still keep the Markov process? And we realize that the solution for this was what we call generalized Gaussian free field or generalized Ising model, in which the probability that phi belongs to d5 was proportional to the product over the edges, or let's say the product over over the vertices of a certain mu d by b. So you have to put a measure on top of the vertices, and then you put on the edges there was this anomalized probability measure of phi restricted to I j ij. So this was just the anomalized Brownian bridge measure. Why it was more interesting to work with the anomalized version than with the normalized version, it was because it has this nice property, which is the only thing we will use today if we manage, is that going from phi I to phi j. So it's like a Brownian bridge going from phi I to phi j, but in which the total mass is not 1, is essentially exponential of minus the distance, and there is a length here. Yes, so one has to put a length. And the nice thing about this is if you were going from x to y at time t with this measure, it is the same as picking a point in the middle at time t1, let's say, it's equal to time t1 times the probability starting from c and going to y, and time t minus t1 of the path between time t1 and t times this. Okay. So it has this nice decomposition, which was one what would expect. It's like if I want to go from x to y, I can go from x to c and from c to y, and of course I'm normalizing it such that I can integrate over all c using the vector. So this gives you the Radon-Nikodym derivative you want. You can recover everything you want out of the renormalized measure from here. So mostly what was interesting, so there were two things. So the first one was saying, okay, this type of measures satisfy the Markov property even for the metric graph. And we use this decomposition for that. And then we try to extend to which type of sets the Markov property was being held. For that, we define filtrations indexed by closed sets, and we saw that essentially one could define stopping sets, and the stopping sets satisfy the Markov property. And we could, for example, deduce from that the FKG formula. We could deduce from that this excursion decomposition, quite a lot of funny stuff. But furthermore, we realized that having the Markov property, which we realized there were many ways of stating it, but having the Markov property immediately implies this. So essentially, the Markov property is giving you enough equations to simplify and to really quite a lot reduce the degrees of freedom that your field itself has. So that's mostly what we did last time. What we want to do this time is to try to do something similar, but now when the graph is also random. So okay, I did my best effort to draw a planar map. So let me start discussing. So let us work with planar maps. So now the fun thing is the following. Yes, we want to have a Markov property for a random function on top of a random graph, in a way. And we want to discover it, and everything that we discover has to be Markovian in a way. So we will start with the undecorated case. We will imagine that our function is constant or there is no function. So we will start with a planar map. A planar map is a two-dimensional, is something like once it's here. It is a two-dimensional, so it is a graph embedded I'm always going to embed them in the sphere with a map edge. So my map edge, I'm drawing it always like this, up to continuous deformation where edges don't cross. Okay. So I hope all of you have seen before what a planar map is. I try to do my best with the drawing. So in particular here we are going to work in the case where my map is always going to be 4 regular. So these are my vertices, and this is my root vertex. So all the maps are going to be for regular with boundaries. With a boundary. Okay, so the boundary is the root vertex, which can have more than 4 edges coming from it, and that's going to be important. So most of you maybe have seen quadrangulations with boundary. So this is the dual of quadrangulation, somehow makes life easier. It's much easier to draw things that are quadrangulation, that are for regular than quadrangulations in a way. So if you look at the dual of this, you will see every vertex here is a square. One has to be a little bit careful because look at this one, it has 1, 2, 3, 4, but one edge is the same. So one has to think that it has 4 semi-edges, so 4 edges. One is coming in and the other one is coming out. That counts as 4. We need it, if not the Markov property would not be true. So one has to play a little bit with this. Okay. So is it clear for you what is a planar map? I'm working with things that are for regular. It's completely unnecessary for everything I want to do, but it really, really simplifies all the computations. So there is an operation here, which is the gluing operation. So first, to define the gluing, I have to define what is a planar map with holes. So we are always going to start with, let's say that we have 6. So this is the root vertex.
Is the root allowed to have connections to itself?
Yes, yeah. I think this one has. No, it doesn't. But it is.
Really? It can. Okay.
Is multiple edges allowed?
Yes. So I'm counting. So in this case, it's only the root that can have multiple edges between itself. But multiple edges between 2 vertices like here are allowed. Okay, so what's going to be the gluing? So from now on, every vertex has to have degree 4. So if I discover a vertex, I know it has degree 4. Let me, I made a mistake, okay. I make this one degree 4, this will be with that. And imagine that in a way we just discovered this. So what will be, maybe I want to do something. Things have to be even. There is some kind of parity thing, doing the fact that I am using for regular graphs, so every vertex has to have an even amount of edges coming from it. So in particular, the boundary always have to have an even amount of edges. So I'm usually going to speak about semi-perimeter, not perimeter. It's small. So this one has to have 6, 1, 2, 3, 4, 5, 6. So this cannot be connected to that one, but this one is connected to this. Is that correct? Yes. So let's imagine that we have this. Okay, maybe you don't want to. Okay. But here, so what is a map with edges? So it looks like I'm just drawing a map, but somehow these ones I still haven't discovered. So there is something here with length equal to 2. Okay, so a map with edges will just be a map in which some of the vertices are going to be marked, and I'm going to think of these vertices not being discovered yet. So they don't have to have any given edge number. Okay, so here I have 2, so I have to glue it with something of degree 2, so it will here. Okay, so this is and it has 2 edges. So I'm gluing it with let's say. So this is going to be there. This is a map of degree. It has 2 here. So the root vertex has degree 2. It can be glued with something with a hole with degree 2. Yeah. So this could have 2 holes, for example. If I erase this one, I could put 2 holes here, and then it would have to be glued with not with one map but with 2 maps.
Can you discover just an edge, or do you have to discover all of the edges connected to it?
So every time you look at a vertex, you see that that vertex has degree 4.
Okay.
But you don't discover where the edges are going.
Okay.
You just know it has 4 edges. You don't know what are the connections between the edges. Okay, so for a gluing operation, this could be essentially. So there is a way of ordering things here, and one paste this part. Yeah. So let me do it with colors. So it's this. I will, let's say, do. So this one we discover a self one, and this one. So this is the way to glue. I'm gluing the blue part here, so it's a combinatorial operation that allows you to put inside a hole something you haven't discovered. You can glue a map inside it, and the resulting will be a new map. Now, hopefully without holes, and in a way, each hole it has to do with connected components in the embedding. Okay, so if I have a hole here and a hole here, this will not be a hole of size 4; it will be 2 holes of size 2. So what would be? So we have 2 things. No, we learned that there are maps with holes, not only maps, and that we can glue into map with holes. What would be, I think I haven't described anything random, but what would be our map? What should be the Markov property?
Is the thing that you glue in, is it always connected to the rest of the graph just via the root, or can there also
Yes,
be...
everything is, it has to be connected just via the root. So the root...
You cannot have like 2 vertices where you haven't discovered yet, and then you somehow connect them with something new.
Yeah, exactly. So each, things will become, they are essentially separated. So they will not be able to connect except through the root. Usually one sees this through the dual. So one glues into something with a boundary of length, of big length, one glues like a disk inside it, in a way. So that's the classical way. It's just somehow simpler to draw when one is working on the dual. even though it doesn't look like it now, because my drawings are bad, but it would be worse. It would be worse. Okay, so now, what would be the Markov property? So I will state the Markov property without even putting a random measure, and what we will want to build out of it. So the Markov property should be something like this. Should be that.
So the two yellow circled things, they are not actually vertices in the new graph, are they?
No, they are not vertices.
Because they're kind of circular,
Yes.
and I thought, oh, they have only two edges.
Yes, but they are not vertices. They are, yeah. They are somehow says that I know that there is an edge here, but I do not know to what was connected. Yeah. So this is what it's saying. So if one wants to codify it, one puts it like a graph and one marks that as vertices, but in fact one has to think that this thing is just telling you, I know there is an edge here, I don't know what are the connectivity of these edges. Mm-hmm. So okay, so take Q, a random, I still haven't described what it is, a random for regular map with half perimeter. But by half perimeter I mean just how many edges goes from the root vertex. With half perimeter n. On the event that a certain, so this is a map with holes. M is containing Q. Okay, so what do I mean that the map M is containing Q? I mean that my random Q can be written as a map glued with certain things that, let's say, I like to write them like Q, M, H. So my example, there was one connected hole, but there could be many. You could glue in many parts. So the map can be described as a map glued with something, and this something has to have a given law. Independent random regular maps for random for regular map with boundary the size of the hole. Okay, so I am indexing my holes. Here I have one hole. This would be the hole 1 and has length 2. So this could be like what one would imagine. Like if I know that I have a given map, that my map contains a given map with holes, well, I could write my map as this map with hole glue with certain things inside, and what one would want is that these things inside has mostly the same law as the beginning. That would be a reasonable hope for a Markov property. So essentially, so this is not a result, not a proof, it's just like an intuition, but we will make it a proposition. So essentially, what do we need? So we need not one measure, but a sequence, like a collection of measures indexed by the side of the length of the boundary, or half the length of the boundary. So Pn measure on 4 regular maps with half boundary or with boundary 2f. So now this would be our Markov process. So let's define Boltzmann map. A Boltzmann map will be just that the probability that my map is equal to a given map is proportional to Q number of vertices. So yes.
Sorry. this map can have more than one boundary point now. The second cube, in principle, or
Yeah, so
one boundary point for each hole.
it's yes, it's one boundary point for each hole, because in a way I make disappear the boundary, you know. So the boundary, the boundary point or the root point, you will cut it and then glue, because there are so many edges. So like if this one has 6 edges, the root one, and you have to glue it into 6 other edges. So you are killing this mark vertex and using it just to glue, using it as just a connectivity. So you get one base one for each hole you have.
Okay, yes.
Yes.
But they are actual maps without holes now.
Yes. So the result of this one would be a map without holes, and this one is maps without holes, this one is with holes. One of course could glue with maps with holes, and then one could play the game iteratively again. Okay, so a Boltzmann map would just be the probability that of a given map is proportional to a certain parameter q, that let's say belongs to 0, 1, but it has to be, in fact, much smaller than 1 for this one to be a well-defined object. Times, so this q to the amount of vertices that I have. And I claim that, so this p depending on n, okay, so claim if q is the Boltzmann map, is Boltzmann, then q satisfies the Markov property. Okay. So I'm going quite quickly here in the sense of I wrote this, but I didn't write what values m is allowed to take. Yes. So m, of course, is a 4 regular map with boundary size 2L, or with half boundary equal to L. Yes. So this is the acceptable things that I am measuring with this measure. Okay. So what I claim is that these ones they satisfy the Markov property. And how does one prove something like that? So essentially one is to say what is the probability. I have to look at the probability of the intersection of the event. So let's see if I can. The probability that QM H is equal to MH, let's say, until that H and M is containing Q. Well, this will be equal essentially to the probability that Q is equal to the gluing between M with M tilde. And this is just proportional to Q to the vertices of M. So for the vertices of M, of course, I'm not counting the yellow vertices, times Q times the product of H to Q to the vertices of MH. So it's just because I'm counting, so the amount of vertices, so when I'm counting vertices, I'm only counting the interior vertices, I'm not counting the boundary one. It simplifies this computation. So essentially, I will have everything written as a product. So it's the product of the vertices on the map with holes, and the product of the vertices of the things that are happening inside the holes. So that implies, by what we did last time, according to the conditioning, that mostly that the conditionally on this event, well, the law is proportional to that product, and being proportional to a product in which there are no other constraints on MH implies essentially that you are independent and that your law is also proportional to Q to this number. So that means that essentially you satisfy the law. So what we have managed to analyze is a certain map, a certain law of maps that satisfies the Markov property. So let me give you two other basic properties that this map satisfies, and now and after that I will go down to L and do a nice a nice corollary of this Markov with Markov property, or in a way try to visualize it much better than the work I have done now. So it goes as okay, so so that's for some map. So properties. So what would be the? So the first one is that they are they are reroute invariant. So I'm going to just say this orally, but it's clear if you change the root edge to another root edge that stems from the root vertex, the law will be the same, because after you do the routing, the resulting map has the same amount of vertices that it had at the beginning, and the probability is just proportional to the amount of vertices. So that's nice, yes. So the second one is that they are uniform when fixing the amount of vertices. So if I fix the amount of vertices my object has, then the law has nothing else to see. Yes, because my law only depends on the vertices, so that means it's uniform on that object. So now, let me do some corollary of the Markov property. So imagine that someone tells you, okay, you have a map, a Boltzmann map, which has a boundary parameter equal to, let's say, 6. Okay? And now it has one mark edge, and you want to discover what is connecting to this mark edge. So I think that there are two possibilities. Either you are connected to a vertex you have not seen, or you are connected to a vertex you had seen, and the only one you had seen before is yourself. So you are connected to the root edge. We are going to treat these two cases separately. So let me define T1. So because this is a type 1 object of L, so this will be the following map with holes. And here I have L minus 1. So, and all of these ones, I still haven't discovered what it is. Okay? So what the Markov property tells us is that the probability that my map is equal to, so I have at the beginning a map, I have the beginning a vertex contained to the root edge, that's T1, glued with any other map, where this is equal to the probability of T1 L contained in Q times the probability that Q is equal to I1L, so that's blue with M, given that T1L. Okay, so here I did nothing. Okay, so what I'm saying is that the probability that a Q is a given object in which T1 was contained will be the probability that of obtaining a T1. What does this mean? It means that the probability that the edge, the root edge, is connected to two different vertices, so the root 1 and a new vertex here, times, well, the same thing conditionally on that. Okay, but conditionally on that T1 is containing L, then this M, yes, is just a Boltzmann it has the law of a Boltzmann map, yes, where now notice that the boundary changed by 2. So I erased 1, but I added 3 new, yes. So this is exactly the same as the probability. I will call this type 1. I just discovered something, meaning a type 1 means that after I discover the vertex to the root, the edge of the vertex attached to the other point of the root, then it was a new vertex. I just call that type 1 times the probability, but now L plus 1, that Q is equal to. So this is called, so I call this peeling of type 1. If you have seen about discussions about random planners before, you see like, okay, I do a peeling of the root edge, and I discover, people would say a new face, I would say a new vertex. That's one possibility. Of course, the second possibility is that I discover that the vertex was, that the edge was connecting the vertex to itself. Okay, and there are many ways of doing this. So I define T2, L1, L2, with L1 plus L2 equal N minus 1. So this would be, the picture is as follows. Here I have L1, here I have L2. So all of these are undiscovered. Okay, and T2 is going to be T2 0 L minus 1. Okay. Just when I have 0 inside here, I will just call that T2. And so now note that when I separate like this, I create 2 different holes. I have to fill in the hole inside and the hole outside. So what is the probability that my planar map can be written as T1L, sorry, T2, L2, L1, L2. Glue, now I have to glue with 2 different maps. H. So this will be, by doing the same computation, it will be the probability of doing a type 2, meaning that this thing is contained of L1 and 2 times, well, I have 2 independent Boltzmann maps, each one with different boundary lengths. So one will be, so this is, sorry, it's 2 L1, and this is 2 L1. One coming from L1, times probability L2, Q equal to 2. Okay. So this is somehow a way of doing things step by step. Instead of doing everything together, we could have done it step by step in the way that I will uncover. I first uncover the edge, the root edge. I uncover the other vertex from the root edge. There are 2 possibilities. This gives me one law, and then inside each of the holes, so I either get a new vertex in which I still keep one hole, but the boundary length went out by 2, and I still have a root edge, and I discover the new root edge, and I can continue discovering like that. Or when I discover a self-loop, this self-loop separates my space in 2, yes, which reduces my total boundary length by 2, and inside each one of them I can continue playing this game. So this is a way of discovering a planar map, in a way. And this way is known as peeling, and people have used these peeling techniques in really different type of ways. Due to the fact that this is root invariant, you could also peel any other edge. And the probability of seeing either a vertex or a self-loop is the same for any of the given edges. So this is a way of discovering your map. And it's a Markovian way of discovering your map. And this is like the classical way of doing things. The classical way of doing things is starting with the peelings, and then try to define a random peeling in a way in which if you see this thing, you will peel this edge instead of peeling that one. What we don't want to do is that. So we have two different directions here. The first one is to try to describe the strong Markov property. Now, for these maps, which is what we are going to do a little bit fast, because it is quite similar to what we did last time. And the second one is to ask how unique are Boltzmann maps in the sense of having the Markov property. So let's start with the strong Markov property. So what do we want to do now? We want to say which random submaps have the Markov property. Okay? So we know that if I peel just one, then I will have it, but somehow one would want all of them. One way would be like, an intuitive is like, okay, I peel the root of the edge. If I see a vertex, I will peel then the seventh one, and I do like an algorithm, and this algorithm can use independent randomness also. And if one thinks about it, this should also satisfy the Markov property. And doing something like that. This is called randomized algorithms, and they do satisfy the Markov property. But this is not exactly what we want to do. We don't want to describe it like this because, as you can imagine, our goal would be to work with metric planar maps, in which essentially one puts random length on the edges. And in this case, trying to do an algorithm would not work that well because it would have to be like in a really big space. One doesn't want to work with problems of measurability. So a natural way would be to define a filtration. Okay? But the main question is what do we index filtrations by now? And that's always the hard part of showing a strong Markov property, is in fact knowing what do we have to index our filtrations by. At the point where we realize this, then essentially everything we learn and a Markov process course goes exactly the same way. So essentially we need a partial order, and the good way of ordering things is working with maps with holes here. So we need filtrations. So filtrations are Q is M. M is a map with holes. So as you can imagine, map with holes by the gluing operation can be partially ordered. If I can glue a map with hole to another map with holes and obtain a new one, then one is smaller than the other, as before. So then, if M1 is smaller than M2, it implies that f of M1 contains f of M2. Okay? So what's going to be a stopping map? So a stopping map is going to be a random map with holes. Let's call it M. Okay, and so we will not put the first condition. The typical condition that one could imagine is that the event that M is contained in a given Q is, so in a given map with hole, is an M measure. Okay, this is the typical thing. We need to add another thing because we are working in a random domain. So we have to think that our domain is random, and we want our stopping maps to be always contained in our domain. This is not something one has to do when one is working in a given graph, because one always knows that the subset is contained in the given subset. So it's a random map with holes. M is a stopping map. And here one has to add a funny thing for Q. So one has to fix the domain one is working with, the random domain is working with. So it's we need that M almost surely M is contained. And of course, one has to say that Q is an F Boltzmann map. So one has to say that the event that Q is containing in Q, this is SQ measurable. So this is adaptability, and then one needs independence of increments, and independence of increments, it just means that you satisfy the Markov property for when one condition on FQ instead of on this event. Conditionally on FQ and the event that Q is containing Q, so one has to add additionally this event, because if not, it's not true. I can write Q as, I don't know why I put small q, okay, I already put small q. Small q, so this small q is not the small q of the parameter of the Boltzmann. I will change it, it's an M. So this is the, so when one does it in LaTeX, there are many different q's one can use, but in real life, there are no QH. So when one conditions on not only on MQ but also on FQ, one gets of course the same decomposition, and the law of this one, these ones are independent Boltzmann maps with the same parameter Q. So essentially, I'm not saying that I only satisfy the Markov property when one condition on this event, but also I can add also the information I'm seeing in FQ, and I'm not winning anything else. Okay? And then this is the right setup. When one works with this setup, and I leave this as a work, but it's based on what we did last time, then if Q is F Boltzmann, and M is an F sloping map, then Qm satisfies the strong map. So that means that if that I can decompose Q as M glued with this QH M, where these QH M's are both conditionally on M, these QH M are both independent Boltzmann map with the right boundary length. And as before, so this I said before, and just announce it. So there are two things, important things I want to say, but I will not want to prove. So the first one is that these are all the possible Markovian, all the possible maps that satisfy Markov decomposition, meaning the following. So if I have a couple that satisfies the strong Markov property, in the sense you can imagine, then I will be able to find a filtration such that both Q is F Boltzmann and M is F stopping. And furthermore, and more importantly probably, is that these maps are more general than they algorithmically generated. So I describe algorithmically generated maps as these maps that can be attained via a peeling procedure, in which I take random decisions, let's say, with a source of randomness coming independently. However, not every map can be built like that. Not every stopping map can be built like that. There are nice examples in which essentially, so I will you have, so this is your map, let's say, well, your map, they have a cut point here. So essentially, so that your map is leading here, here. So there are some nice examples in which essentially you can show that this boundary, this is a stopping map. However, you cannot obtain it via an increasing sequence of stopping maps. Okay? So you can, if you add 4 at the point at which, so you can do the first step, the second step, the third step, but at the fourth step, you are forced to have to not have a stopping map that comes out of this. Okay? So essentially, you have these stopping things that just appear. They Markovianly decompose it, but they cannot be constructed locally. So that's another reason to try to generate these theories, because they are all the ones you are interested can be constructed via filtrations. So this is a really general type of idea. If you have a good Markov property, just take find a good filtration which is hinted by the Markov property, because the Markov property is indexed by something. You are saying, like, conditionally on this, I have this law. So after you properly write your weak Markov property, your strong Markov property comes for free, because you will decide what your filtration should be and everything essentially. But the most interesting thing, of course, would be the uniqueness. Even though the most useful thing is the strong Markov property, I would, for the idea of this course, I would claim that the most interesting thing is whether the Markov property can or cannot characterize the law of our object. Or said in another way, can we characterize all the probability laws on planar maps that satisfy the Markov property? I don't want to exactly do that. I will do a slight different change. So essentially, what we are trying to model is really a randomly chosen domain. I don't want that my domain depends exactly where my root is. Okay? So it is quite reasonable to say that I want something that has the Markov property, but also is root invariant. Okay? So I will add this. So this is 3. So this will appear in 3, and this is 2. So what we will prove, and this is the theorem I will write, is that if I have the Markov property and I am uniform when fixing the cardinal of V, or if I have the Markov property and I am root invariant, then there will be a Q such that I am a Q Boltzmann. These are the only reasonable things that have the Markov property. Okay? And I mean reasonable because the root invariant. If not, I could try to tilt by the root and life would be a little bit not that nice. So in a way, this would be like homogeneous Markov process that would be like in a certain analog. Okay, so proposition, or I would call it theorem. The Q. No, okay. So what do I need? For this, I need a collection of measures indexed by the boundary length, Pn, satisfying the Markov property. Recall that the Markov property was not making reference to one probability measure, it was making reference to a collection of probability measures indexed by the boundary size. As the classical Markov property makes sense to a collection of probability measure indexed by boundary condition in which your process starts, or the starting point of your Markov process. So let PL satisfying the Markov process satisfying the Markov property. Doesn't matter if it's weak or strong, yes, because both imply each other. Property. Then the following are equivalent. Equivalent one. There exists a Q such that PL is Q Boltzmann. Note that the same Q for each L. Q Boltzmann. The second is that PL are uniform when fixing the amount of vertices I have. And the third one is that PL are a root invariant. The routing invariant. Okay. Sorry, I wrote it, but the 2 and 3 are this one. Okay, so mostly, so probably 2 implies 1 is the thing I'm most excited to show in this whole talk. So it is. It comes out of a quite nice proof idea that is based on this, in a way, this separation of variable methods to solve PDEs. So it's quite a weird thing, but I think you will see it. So so clearly 1 implies 2 and 3, and the way the proof goes is that you show 2 implies 1, and then you prove 3 implies 2. So to prove 2 implies 1, you need to find the Q. Okay? So this is the main technique. How do you find which is the right Q? And the Q is essentially punishing you for having a phase. So you have to compare the probability of a map with the same map but with a new phase. So let's define Q that will depend on L and a map. And the probability, so this probability measure someone gave it to us, of having, so here I have to be with one thing here, glue with a map to get the probability of the same map. So let me do the drawing here. So imagine that, okay, I'm really bad at drawing maps. So the main thing is, so here, and then you have here the old map. So your old map was doing something strange here, okay? So what we did is we added this thing, that the only thing it changed is that it added one new vertex. Sorry, I redrew it really badly. So this is not what I want to make. So here I have L. Here I add a new vertex. To this new vertex, I will add a loop, and I will put this as a 0. So these are the holes for each space. So I think I did everything hopefully. Okay. So let me. Is this? So you start with the vertex. Yes. So you do a new vertex. This new vertex comes with 3 new edges. No, each vertex I arrive, it comes with 3 new edges. I glue one to itself. So I have one new vertex, and now it is the same as I had at the beginning. I have the same L edges here. So I can glue everything. So a priori, this Q depends on both L and the map M I came with. So let's show that at least it doesn't depend on the map M it comes with. So what's the probability of L of this glued with M? Well, one can check that this object can be built out of, this is gluing so first I have to discover a vertex, and then I have to glue a vertex to itself. Yes, so an edge to itself. So this is T1 glued with T2. T1L and T2L. Okay? So I have to first discover a vertex, and then I discover that the root edge was glued with itself. So okay, so this means that using the Markov property, I have to first have a type 1. I first discover a type 1. Now my boundary length is L plus 1, or 2L plus 2. So, and then I discover a type 2 with length 0 and L. And then I have to discover the map itself. Q. So I'm writing the probability of M, meaning the probability of Q is equal to this. Okay? I hope it was clear. So given I fix a given map M, I fix what's the probability that the map I obtain is M, the ratio between that one and this specific map. And I claim that if Q existed, this should be exactly Q because this one has just one more face than the other. But what we learn is that the Markov property implies that this QLM only depends on L. Yes? And now the thing we have to show is that this QL is independent of L. So let us show. So that QLM is equal to QL. We need to show that QL does not depend on L. Okay, to do that, recall that we know that the probability of the maps that have exactly the same amount of vertices is always the same. Yes. So we could reduce on the maps with boundary maps with boundary length L, we could reduce one phase using this QL. That was the trick. So after using one of my operations, I just added a new phase. Yes, so that means that if I have a map with boundary length L, and I want to know its probability, or one with one more phase, I just paid a price of QL. Yes, because I gave you one example of a map that has probability QL less, or times QL, but all of them had the same probability. So what I claim, I will write it as if they were a human being. So we, by uniformly distribution, by 2, we know that the probability of a map L, of a map Q equal to M, this will be proportional to Q L to the amount of vertices of M. Or if you want, because the probability that Q equal to M tilde with one more vertex, with one less vertex, let's put vertex, this is equal to QL. Okay? So I was doing the ratio of two things. Yes, one with one more vertex than the other one. But we know everything with the same amount of vertices has exactly the same probability. So I could have used any other object with one less vertex. And this ratio is QL. So that means that the ratio between any two ones is the difference between the amount of vertices they have times the amount of QL. And then, because this is a probability measure, and I can sum all of them and get essentially this. Okay. Or in another word, let me, if that was not clear, we will say that the PL is equal to M, is equal to QL to the amount of vertices of M, divided by the sum over all possible maps of QL to the cardinal of the vertices of M. So now we want to play the game again. So the game goes as follows. So Pl of so this was Q equal to P1 glued with P2 glued with M. So this one, this will be equal to Q to the vertices of M. So this is the one that I don't drop, the vertices of M plus 1, divided by this sum. So let's write this sum. I will not write it as partition function because I will have partition functions coming afterwards, as a W of L, W that depends on L. Yes. But we could have done one peeling. We could have discovered one peeling because okay, so here's QL. So we want to relate QL with a different QL, with QL plus 1. Because if not, I cannot never say that this does not depend. And we have a technique, the peeling of type 1 allows us to make appear PL plus 1. So this will be a peeling of type 1, PL of type 1 times PL plus 1 of Q equal to T2 blue with M. Okay, but now, when this one has a new vertex, so this has Vm vertices, but most importantly, we can do the same argument we did for QL, works for QL plus 1, of course. So this is equal to this probability type 1 times QL to the vertices of M, QL plus 1 divided by the partition function of N plus 1. Okay, here it is the magic. Okay, so here I think I have finished. Why? So let's rewrite the board. So the board tells us that QL divided QL plus 1 to the amount of vertices of M is equal to WL divided by WL plus 1 times QL divided by QL, I think. Doesn't matter that much, times probability of type 1 starting from M. Yes. So the left-hand side does not depend on the vertices of M. But the right-hand side does depend on the vertices of M. That means that the left-hand side has to be constant. And it means that this ratio has to be 1. So then, 12 equal to 12. Well, so that's 2 implies 3. And I think this is a good stopping time.